Hey everybody, welcome back. In this video, we are looking at a different way to construct a solution to a differential equation. We talked last time about what it meant to be a solution, and that in some cases we're lucky enough where we get an explicit formula, an explicit way of representing the function as an algebraic expression that would be able to tell us exactly what our solution looks like. Now, there is another way to represent solutions, and this is oftentimes where we have to resort, or what we have to resort to, in general applications, because we don't sad news. Not all, the vast majority of differential equations cannot be solved explicitly, and yet we still need to know what the general behavior of solutions to these equations look like, if those solutions even exist in the first place. So, what I'd like to do is show you a different way of considering what a solution looks like. And this is where one of the prerequisites from before come in. You might need to know a little bit about what a vector field is first. So what I'd like to do on this page on the right is give you a quick introduction, or a crash course, if you will, in what a vector field is. So just like we have functions that take in a number and spit out some other number, and we have graphs for these, and I can do that graph in a different color, so yay! There is a rough sketch of what this function looks like. Now, that is a function of one variable that spits out a real variable, or a real number. And what we're going to do here is change this up a little bit and say, okay, let's say I have a function of two variables. So let's call this guy g of x and y. Awesome. I can have a representation of what this guy looks like. And if I'm careful, I can do this very quickly. This would be the 0 level set. And let's see if I can figure this out on the spot. If y is positive here, that would be the negative, so I believe that would be what a -1 set would look like, and that's what a 1 set would look like. I can represent this function as either this contour plot, or I could be really cheeky here and show you that this guy is basically just a saddle, or represents a saddle. And that would be effectively another way of representing what this function looks like. But it's a function of two variables that spits out a real number. Now, in multivariable calculus, toward the end of your multivariable calculus course, you will also be introduced to the idea of a vector field. And this is where we have a function that takes in multiple variables and spits out multiple variables. So let's say I did something like this, minus x by y. So I have a vector for an output. And how we usually represent these guys is by, well, let me show you first of all. So let's say f of 0, 0. F of 0, 0 is going to be, well, a -0 by 0, so it's just the 0 vector, which I'll denote by 0 with a little vector bar over the top, or an arrow over the top. So at the origin, I'm going to put the 0 vector. Well, let's do another one. Let's say f of 1 by 2. So it means x is equal to 1, y is equal to 2, so I have -2 by 1. And if I plot over 1 over and 1, 2 up, then I have a vector that begins at 1, 2, but points over there. And that would be exactly what this is representing. This is a vector that points, well, maybe it looks a little long. Let's make sure I do this correctly. Go ahead and let me know how good of a job I'm doing here in the comments. Woo, there we go. So that's a more appropriate vector, that this is a vector based at the input point, and just tells us that there is a point, there is a direction and a magnitude associated with that point. Right, and we can go ahead and actually continue this vector field And I chose a very specific one because I am very familiar with this vector field. This is actually what's called a circulation vector field. This is the counterclockwise circulation field. And you can put in any input in the xy plane and out pops a vector, and you can go ahead and base that vector at the input. And this creates a field of vectors, hence the name a vector field. Now, what does this have to do with differential equations? Well, if you follow me for a moment, yeah, come on down here, come on, yep, a little bit further, yep, right there, okay, good job. Now, if you come down a little bit further, there is this idea that in many applications, we can write our differential equation in this form, where the derivative can be solved for explicitly. Not all differential equations can be solved like that. For instance, consider dy dt equals e to the dy dt. Good luck trying to put that in this form. Ain't gonna happen. But the point is that I can go ahead and think about this in terms of this dy dt, which is nothing more than the slope of y of t. Now, think about it like this. Let's go back to our example of a body in free fall. So this was m dv dt is equal to mg minus gamma v from before. And I can go ahead and solve this for dv dt, g minus gamma over m times v. And I can see, oh geez, there we go. I can see that if I plot v versus t, then at any point in this v by, or this t by v plane, that there is a derivative associated with this function, which would be f of t by v, but really we're kind of ignoring this t term. This function does not actually depend on t explicitly, but we include it in what's called the rate function to begin with. So this is called a rate function, but it is acting as a slope. And if I plug in specific numbers here, or let me go ahead and not blow that just yet, notice that if I'm over here, t doesn't really matter, but if I'm looking at v, which is a positive number, that means that I will have a negative slope associated with this positive v value. And if I, is that right? Did I do that right? I think I may have messed that up a little bit from before. I'm following my notes, not my video. I think it was a minus v. There it is, yeah. So this guy, if I'm above, there we go. Then it's, yeah. There is a value here where all the slopes are 0, right? And I can actually check what that is. You can verify v equals, what's it going to be? Minus gamma over mg? No, minus mg over gamma. Right, and that's just solving for f of tv equals 0. But if I go just below that, if I look right here, well, then I'm going to have a smaller value. Oh, that should be, no, sorry, that should be a negative number. Haha. That should be down here. This is what happens when you do math off the cuff, right? Scripts be damned. Okay, there we go. So if I go a little bit higher, so that's going to be this down here. There we go. If v is a little bit bigger than that, I'm going to have a positive slope for all these same values of t, right? This function doesn't depend on t. If I go to a higher velocity here, no, these should be negative numbers. Oh, again, this is what happens when you do math off the cuff. Negative slope, negative slope, negative slope. Right, but at each point, the point is here that there is a slope, very much like a vector field, because that's technically what this is representing. There is a slope associated with every single point in the plane. And what we can do is specify where we want that function to start, and our function has to be tangent to each and every one of these curves, each and every one of these slopes. And it turns out that we can represent our solution as kind of a good guess more than an explicit equation. So we see in this particular instance that there is what appears to be some velocity that our object wants to gravitate toward. Pun definitely not intended, but take it or leave it. This body in free fall wants to approach some velocity, some eventual. There should be a word for this. Let's go ahead and call it terminal velocity. And this is exactly what happens when you set your rate function equal to 0. Because what's really happening there is you're saying dv dt, the acceleration, is 0. And physically, that means that the gravitational force is exactly balanced by the drag force in our free fall model. So this is another tool that we can use to represent solutions to differential equations, and this is a graphical representation. It's going to give us a lot of visual information, a lot of geometric information about our solutions, where we didn't actually have to use any sort of calculus in order to solve it. So bear that in mind, that we can actually figure out what solutions might look like, even if we can't figure out what their explicit analytic representations are. And this is exactly the sort of thing that we come up with, that we see what's called a slope field. All these different red slopes here are acting like a vector field and telling us where our solution needs to pass, how it needs to pass through these different points. And it creates these nice visual representations of our solutions. And we will notice, hey, solutions don't actually intersect one another in these diagrams. Very curious. Well, maybe we'll explain that in a little bit. Well, let's see. We call that a rate function. We notice that there is a solution here that's totally flat, and that's what we call an equilibrium solution when the rate function is 0. And there are various interpretations of what that equilibrium solution is in context. So this is usually a construction that we leave up to a computer. So we'll talk a little bit about numerical approximations of solutions very, very soon. But for right now, I think we should go ahead and kill this video and start talking about how we can actually construct some solutions analytically, kind of like